going to derive the reduction formula for cosecant raised to the nth power of times dx. And the result is below us, and we are going to prove that it's not wrong. The integral of cosecant nx dx, which I'm going to call I, we are going to break off two factors of cosecant x. So instead of n factors, it's going to have n minus 2 factors. But I need to multiply it back. Hence the term break off. Now we're going to use integration by parts. I choose to call that piece u, and I'm forced to call what's left over dv. Part of it is u, and the rest of it is dv. I guess you can pick dv first, and then what's left over is u. But in the end, once you call something u and something dv, there shouldn't be anything left over. So u is cosecant n minus 2 of x. So du is, well, you have cosecant of x, and you're raising it to the n minus 2 power. So to take the derivative or the differential, you bring down the power, you make the new power 1 less, and then you multiply by the derivative of what's inside, which is negative cosecant x times cotangent x times dx. Alright, now dv is cosecant squared of x dx, and then v would be negative cotangent of x. So now that we have everything, let's use the integration by parts formula, which says that the integral should be u times v, which has a minus sign right there. In fact, I'll write v times du, minus the integral of v du, minus the integral of v du. Now, this minus sign right here comes way in front. That is, this is negative, and that's also negative, so it becomes positive. That is, I can leave this sign just like it is. Okay, now I'm going to write down the n minus 2. I'm going to write down the cosecant of n minus 3 of x times, multiplying by another cosecant. I can add 1 to that power. That is, when you add the powers, n minus 3 plus 1 is just n minus 2 times cotangent of x times dx times v. Remember, we dealt with the minus sign, but not the cotangent x, so I have cotangent squared x. And we're going to rewrite that. Now, this is equal to negative cotangent x cosecant n minus 2 of x minus n minus 2, just copying integral of cosecant n minus 2 of x times another way of writing cotangent x, which is cosecant squared x minus 1 times dx. But this is just perfect. Because when I multiply this by this, I'm going to get back the integral of cosecant to the n of x, what I started out with. And when I multiply this integral by negative 1, I'll have the integral of cosecant raised to n minus 2 of x dx, a smaller power. And that's just what we want. So we have negative cotangent x times CSC n minus 2 of x minus n minus 2 times the integral. But now I'm going to distribute this. So this times cosecant squared x times dx, which is cosecant to the nx dx minus, now I multiply those two times dx, and I get the integral of CSC to the n minus 2 of x dx. Okay, I'll distribute this constant. So this is negative cotangent CSC n minus 2 of x minus n minus 2 times the integral. N minus 2 times the integral, and negative times another negative will be positive. So I get plus n minus 2 times the next integral, cosecant n minus 2x dx. But this is the beginning integral. So on the left side I have I, and on the right side I have negative n minus 2i. When I bring this to the other side, it'll become plus n minus 2i. There's an understood 1 in front of the I. Well, if you have 1 and you add n minus 2, you're going to have n minus 1. In this case, n minus 1i's. So when I bring it over, I'll have n minus 1i's. And I promise to do that. So I have n minus 1 times I times all of this and all of that, with one exception. Not this piece. I just brought this over to the other side. So I will have n minus 1 times I is negative, just copying, negative cotangent of x times cosecant raised to the n minus 2x plus this integral. Now the nice part about this integral is like what I said a few moments ago. The power has been reduced. Okay. But we don't want to know what n minus 2 times the integral is. So we divide both sides by, if I said n minus 2, I meant we don't want to know what n minus 1 times the integral is. So we divide both sides by n minus 1. And now we just know what the integral is. Okay, we know what I equals. But remember, I originally was the integral of cosecant n of x dx. So now we have a formula where the new integral, the power has been reduced. It's still in the same form, but the power went down. You know, if the power was 20, well, you do all this, you get the power of 18. Then you do it again, and you get the power of 16. Eventually, you'll have the power of 4, and then the power of 3. And when you get to the power of 2, well, you better know what the integral of cosecant squared dx is. Okay, this completes this proof of the power reduction formula for cosecant raised to the nth power of x. Thanks for watching. Leave a comment saying how much you liked it or how much you didn't like the video. Make some comments about what videos you would like for me to make. Leave some comments about videos you don't want me to make. Leave comments. And also subscribe to my channel. Thank you. Watch and learn.